just up here on the board from yesterday. I don't know. I told you these two triangles were similar like this. Like maybe if I said this was 4 and this was 7 and I told you this was 12, how would you set a proportion up to solve for x right there? These two things are similar, so they're the same shape, but the size is just different. How would you set up a proportion to solve for x there? It doesn't matter. If you start from small to big, then the next one's got to go small to... Yep. Just like that. Okay, so you're going 4 is to 12 as 7 is to x. So you would go 12 times 7, which is 84, and then you would take 84 and divide it by 4, and x would equal 21 down here. Now think about this, kids. What's 4 over 12 reduced to? 1/3. What's 7 over 21 reduced to? 1/3. So it works, doesn't it? Okay. All right, so guys, what we're going to talk about today then here, we're going to start going away from what do the side ratios look like. The side ratios, well, just set the proportion up. But guys, we start looking at areas right here, okay? Not distance around a figure, but actually how many square units are on the inside. And I want to read this theorem here. It's called areas of similar polygons theorem. It says if two polygons are, what's the word again here? Similar, same shape, different size, then the ratio of their areas is equal to the, okay, I want you to read this right here. It's equal to the what? Squares of the ratios of their corresponding side lengths. Guys, when we answer questions in terms of area, we say, this has an area of blank square units, right? Okay, when we're talking about areas right here, anytime they talk about areas, I want you to think second power, okay? Because areas are a square unit or a degree 2 value, okay? So this formula down here says this. It says if the two polygons up top are similar, KLMN similar to PQRS, then the area of PQRS and the area of KLMN is equal to PQ over what? Okay, do you guys agree if you look at this right here? I'll pull this down here real quickly. But if you look at where PQ is, do you guys see PQ right up here? And do you see KL right here? Are those two sides corresponding to each other? In other words, are they in the same general position? Absolutely they are. They would say that the area ratio is, well, for an area, what do they have to do to that ratio of PQ to QL? They have to take it to what power? Second power. Okay, so anytime you see area, I want you to think what power. And all these ratios would equal to the side ratio to the second power. So here's this example 5. And I think you guys should probably put an example 5 star here because this is kind of important. And I'm going to highlight this right here. We're finding what now, kids? Area. So I want you to think what power. Okay. It says in the diagram, triangle PQT, the one on the left over here, is similar to triangle what? RST. And the area of RST is what? 75 square meters. Find the area of what? Okay, it's not saying distance around anymore. So what this is saying right here, the area of RST is 75 square meters in here, okay? That green shaded part in there is 75 square meters, okay? Now, the way this works, kids, is the following. If we're trying to find this unknown area over here, I'm going to put an X on the inside here. I don't know what it is. I have no idea what that area is. Okay? The first thing you have to ask yourself is this. Do we know two sides that correspond to each other in the triangles? What sides correspond? Or what distances are they? 10 and 14. But guys, that would be just if we were looking for a side that compared 10 to 14. We're not looking for side lengths anymore. We're looking for what? Okay, here's how I think that we should write this, kids. Okay? Guys, if we were doing a side ratio right here, this would be 10 over 14 because those sides compare 10 to 14, right? Okay, so what it means for this, it means for every 10 units of length on the smaller triangle, there's 14 units of length on the larger triangle. But we're not looking for lengths anymore, are we? What are we looking for? If I'm looking for an area, we're going to have an area ratio. And the area ratio is simply the side ratio to what power, kids? Second power. So here's what I'm going to say here, kids. I'm going to say, well, from a side ratio, we can get an area ratio. And that would simply equal 10 over 14 to what power, kids? Okay. Kids, help me with the math. What's 10 squared? 100. Anybody know 14 squared off the top of their head? Oh, very good. 196. Very good. You guys knew that, right? You knew that, right? All right. So, guys, here's what this is saying. Okay. This means for every 100 squares on the inside of the smaller triangle, how many squares are on the inside of the larger triangle? For every 100 squares on a smaller triangle, there's how many square units on the inside of the bigger triangle? Here's what we do. Okay, here's how we set this up. All right. I'm going to take my area ratio, which says 100 to 196. It means for every, and you don't need to draw these arrows, it means for every 100 squares inside the smaller triangle, there are how many squares inside the larger triangle? Okay, but here's the deal, kids. I'm going to set this equal to the actual number of square meters that we know. Which triangle do you know the area of? Small one or big one? Okay. Well, if it says 100 is to 196, we would say as 75 is to what then? X. Okay. So really what we're saying is this. Okay, we're kind of saying, well, we know that the ratio of the small triangle area to the large triangle area is for every 100 squares in the smaller one, there are 196. But the smaller one only has how many square meters, kids? 75. And we're going to put an X down here to find the area of the bigger one. Okay? So here we go. Okay, so what two numbers would I cross multiply first? Oops. And then divide by what? What do we get there, kids? Okay, now this is an area on the inside of this bigger triangle. So this would be 147 square meters there, wouldn't it? It'd be 147 square meters. So kids, if they start talking about area, you need to take your side ratio to set a proportion up. You need to take your side ratio and do what to it? And that gives you an area ratio. Okay? Now that's a tricky concept for kids. Always has been when we first start looking at things like this. So if you get stuck on something, make sure you ask. Okay? That example, are you kind of okay with me on that? Okay. All right. Everybody have what they need right there, friends? Okay. Any questions to this point? Okay. Final example today. It says, decide whether the polygons are similar. So we're looking at determining if G, N, M, H. So start at G, right here. Go to N, M, H, this rectangle right here. They want to know if that and M, L, K, H are the same or similar to each other. Explain your reasoning. Guys, the way the order starts right here, I'm going to do this. I'm going to underline the G, and I'm going to underline the what? M. They want the G and the M to match. So guys, if I did that, G is in the top left right here, right? Can you guys see this rectangle over here? I'd have to actually kind of turn it to make this make sense. So I'm going to break these two off in order here. Guys, I'm going to draw this first rectangle kind of like this. Okay, I'm going to label this the original one, G, H, M, and N. Okay. Guys, do you know the distance from G to N? 10. How about from G to H? 25. So this would be a 10, and this would be a 25, wouldn't it? Okay, now, to make these rectangles kind of match by order, they want the M to match G, they want the L to match N. So this L right here, this L is kind of like this N down here. So what am I going to have to do with this small rectangle on the right to kind of get it to match the order? I have to kind of pull it off from here and then lay it down, right? Okay, so I'm going to draw a small rectangle like this. Okay, and then this would be M. This would be L. Guys, going from G to N to M to H. It starts here, wraps around to H. Going from M to L. Does that kind of go the same order right there? Okay, what's the distance from M to L, friends? What's the distance from L to K? Okay, it says decide whether the polygons are similar. Well, guys, first of all, what's going to be true about all the angles inside of a rectangle? These are all right angles. So are all the angles going to match? We know we're good on angles, right? So if they're going to be similar, corresponding sides would have to be proportional, right? So what's this 10 have to compare to right here, kids? 4. Okay, so we're going to look at a ratio of 10 over 4. How about this 25? What's that compared to? 10. And then this 10 would compare to what here? 10 and 4 would compare, wouldn't they? So and then the last pair of sides would be 25 and 10 again, right? If those ratios all divide out to the same value, then are these two rectangles going to be similar? Well, maybe. Anybody know what 10 divided by 4 is? Or what it reduces to? Won't 2 go into both of these? What's 25 over 10 reduced to? Won't 5 go in both 25 and 10? How many times up top? How many times on the bottom? Oh, we already know 10 over 4 is 5 over 2. And 25 over 10 we already know is 5 over 2. Kids, what's true about all these ratios right up here? Are they the same ratio or are they? They're the same, okay? They're proportional. Those sides are proportional. So we would say similar or not? Okay, I'm going to say sides are proportional. Angles are equal. And it's trying to reconnect here again, kids, it looks like. Give it a chance to catch up, it probably should. There it is. All right, kids, how you feeling about this today? Any questions and notes-wise at all? Okay, kids, I've sent out a big ideas I want you to start looking at. So I'm going to give you the last bit of time to, whoops,